Hi, everyone. Welcome to the webinar. Thanks for joining us this afternoon. I am Anup Divakaran. I'm a manager at Digital Technologies, and along with me, we have Santiago from QU Tools. Dr. Santiago is the product manager at QU Tools. Hello, Santiago.
Hi, hello everyone. Thank
All
you.
right. We also have Mrinalini Barak. She is a quantum solutions engineer from Digital Technologies. Now, I'd like to give you a brief introduction to Digitode before we begin. Now, Digital Technologies is a 7-year-old company. We are a technology solutions provider supporting academia, industry, and research through advanced engineering solutions. We work in multiple domains. We work across embedded systems, artificial intelligence, Internet of Things, edge intelligence, FPGA platforms, and test and measurement solutions. We also enable wireless, RF, 5G, and 6G research using dedicated tools and lab environments. So we also design and deploy complete lab setup with hardware, software experiments, and training with multiple labs established throughout India. We work with all the major engineering institutes across India. We invite you to visit us on our website and get more information. All right. I would also like to set the structure for today's webinar. So we will have Mrinalini take the lead from here and give us an introduction in detail about what we do at Digitode. Also, you would have a dedicated Q&A section at the end of the topics, that is post the presentation and the demonstration by Dr. Santiago. You'll have a dedicated Q&A session to answer your questions. I would request you to hold on to your questions, if any, for that time. Mrinalini, over to you.
Thank you, Anu. So, good afternoon, everyone, and welcome to the webinar. So, I would like you to I'll just tell you about our key solutions which we are offering in Digitode Technologies. And so, at Digitode, we provide a wide range of emerging technology solutions. So, including all these are very new and very trending technologies which we are working on. So first we can see has automated test and measurement solution for high performance real-time monitoring. We have edge AI and machine learning solutions for real-time embedded intelligence. We also have FPGA based design, verification and prototyping solutions, 5G and 6G wireless testbed for next generation wireless technologies, and last, we have quantum and optical solutions for quantum communication, fiber optics, and photonic devices. So now we have collaborated with very known OEMs all over the world. So first, I would like to talk you about the ST Microelectronics. Then we have collaborated with Digilent, QU Tools, Mantis Wave Network, TMY Tech, Crowbot Technologies, Qubrid, and Emona teams. So now I would like to talk about the collaboration between Digitode and QU Tools. So basically, Digitode is proud to collaborate with QU Tools to advance quantum technologies and photonics education. So basically across India, all across the universities, educational institutes. So Together, we enable hands-on learning in quantum optics and photonics, practical exposure to entanglement, quantum communication, NV Center, and quantum randomness. Support for teaching labs, academic courses, and advanced research platforms, basically the workflows using real experimental setup, and guided learning tools. So now I would like to introduce our resource person for today's webinar. We have Dr. Santiago Lopez Vidrobo, and he has a total experience of 6 years in research. He is working at QU Tools as a developer and product manager, and he has expertise in experimental quantum physics, quantum optics, photonics, and generation of entangled photons. So topics covered in this webinar, we will be looking for what is quantum entanglement, single photon interference, properties of photon entanglement, then applications of quantum communication, and then followed by a live demonstration of the entanglement demonstrator board and with an add-on board. So now I would over to you, Santiago. You can continue with your presentation.
Thank you very much, Milani. Thank you very much for inviting me. I am actually very, very excited to be here today. Now I will share my presentation. And of course, thank you very much for the kind introduction. As Milani mentioned, my name is Santiago Lopez, and today I will present one of our quantum educational kits. So let's start. First of all, I would like to put my laser pointer. So in my presentation, I would like to first introduce you to what is Q-tools, what is our philosophy. Later on, I will go immediately to the fundamentals of entangled photon generation. Afterwards, I would like to give you a very broad explanation of what can you do with these entangled photons, what are the technological applications that nowadays people are looking into. After, what can you do with our entanglement demonstrator? What are actually the real experiments that you can perform with our devices? And last but not least, something very important is the extension that you can do when you can actually connect and start playing with our devices. This, we call them the add-ons. And last, I will give you a live demonstration of our device, the quantum entanglement demonstrator. Okay, so I would like to give you first a brief introduction of the history of Q-tools. Q-tools is a spin-off company that was founded in 2005 by the University of Ludwig Maximilian here in Munich, where the company is. The first idea was to develop tools for quantum research. In particular, we developed the Q-tau or the time tagger. After some experience, we decided that the company wanted to not only generate tools for research, but also for education. And this is where we started with our QED, or entangled photons. Nevertheless, one of the downsides of this device was that only very experienced people were able to actually use and manipulate our firstly experiments in this regard of entangled photons. The next idea was, okay, we actually want to broaden our vision. We want to actually educate quantum, what we call it, the quantum natives that actually can be younger students that are going to be able to start exploring and experimenting, and of course, grasping all behind what is actually quantum optics and quantum physics. This is where our portable photonic laboratory came into play, or we call it the quantum coffer. Now, what I would like to present you today is our QEdu quantum kit. This is the latest devices that we have. On the one hand, as I mentioned, we have the quantum entanglement demonstrator, and also the Q nitrogen vacancy or NV centers. How do we actually manage this? Our philosophy is that, as I mentioned, we want to broaden the spectrum of quantum natives. We want to have an accessible, real hands-on experience. What do we mean about accessible? We want these devices to be compact, robust, transportable, where people can use and experience quantum experiments not only in a laboratory, but also in a classroom or in an office or even in a fair. It's a transportable turnkey device, so it's robust. One of the things that we want to do is that we want to avoid these very complicated alignment procedures. We want to have it almost ready to be used. We offer an open source community where, on the one hand, we offer our guided mode software, but on the other hand, we also have this open source software where people can actually introduce their own ideas, introduce their own concepts of how they want to teach this quantum optics or quantum phenomena. So in our philosophy, in a very short way, we make the devices and you are the educators, but we are going to give you all the important and necessary elements in order to give this education to the further generations. Of course, this could not be possible without our partners, which is Enhance, that makes all the electronics, the firmware, the software, and also the MIT or Made in Turingen, where they do all the drilling, miling, and assembling. We want to really say and thank our very close partners. Let's now go directly into the quantum phenomena. We offer, on the one hand, the spin-off NV centers or the nitrogen vacancy center, which what it is that we do it in diamonds and we replace a carbon atom with a nitrogen atom, and we also introduce a vacuum or a vacancy. With these experiments, one can perform electromagnetical we can actually explore, not perform, explore electromagnetical characteristics of this NV center. Why is so important? Because this NV center behaves as a single atom. If it's a single atom, can also be a single photon source. With these, as I mentioned, with our experiments, you can explore, play, discover, and learn all these optoelectromagnetical properties that you can perform with these nitrogen vacancy centers in diamonds. What is important for today is our photonic entanglement. This is a correlated photon source generated by nonlinear crystals that are going to produce entangled photons in polarization. So let's go a little bit deeper into it. What is parametric down conversion? Parametric down conversion is a nonlinear process where an incoming photon with a certain frequency omega p interacts with a nonlinear crystal chi2. In this interaction, this incoming photon is going to be annihilated, and immediately after, two daughter photons are going to be created, which are namely called signal and Euler. Because this is a nonlinear process, the energy must be conserved. Here I show you the intensity versus frequency, where these poles, which represent the incoming photon, is going to translate the energy into two daughter photons with lower energy. This is what is called the energy conservation. Since this is an interaction of light and matter, there is going to be some dispersion. In this dispersion, what is called the phase mismatch. Here you see this delta K, which represents the Poynting vector of the photon, the signal, and the Euler. Because they have different frequencies, they also have different K vectors. Of course, in order to make this process efficient, this delta K has to be nearly zero. And this is what we call it, the momentum conservation. Now, there are the different type of processes in this parametric down conversion. On the one hand, we have the type 0, which corresponds if we shine our nonlinear crystal with an horizontal polarization state of the photon, what we are going to create is, again, two daughter photons with the same polarization state. Type 1 corresponds to if we shine the crystal with H polarized polarization state, then we're going to get the orthogonal, which is going to be the vertical. And type 2 is when we shine with an horizontal polarization pump, we're going to get an horizontal and vertical. Now, why these correlated photon pairs or biphotons are so important? Because they can be applied in very different technological procedures, like in quantum metrology, quantum communication, and quantum sensing. However, it's not only sufficient to just create correlating photon pairs. They also need to fulfill very demanding and very specific characteristics in order to be served for these technological applications. For instance, they should be tunable, they should have large frequency separation, and also sometimes they have to have broad bandwidth. In my presentation, I would like to focus on these quantum communication criteria and applications. Let's go to the core of our entangled photon source. Here, what do we have is an incoming laser centered at 405 nanometers. Here we have a halfway plate, a YVO crystal, two BBO nonlinear crystals. This is where we generate the parametric down conversion process, another YBO crystal, and of course, optical fibers to detect and to translate the photons and later on being detected by single photon detectors. So in this animation, and of course in this direct notation, you can see that we start with a vertical polarization state of our pump photon. With this halfway plate, we can rotate the polarization state from vertical to diagonal, and therefore we can represent this diagonal polarization state as a sum of vertical and horizontal. With this YBO crystal, what we do is that we dephase these vertical and horizontal polarization states in time. And why we do want to do this? Because we want to create type 1 SPDC process in one of the crystals and also in the other one. That's why here we have this H photon corresponds to the generation of BV SPDC photons, and then this V photon, incoming photon, corresponds to this HH. What this last crystal does is that we're going to have coherently superposition of vertical and horizontal photon pairs. But what does that mean? What is this coherently superimposed pair of photons? What we're going to create is what is the so-called Bell state. What is actually a Bell state? Bell state is a maximally entangled two-photon polarization state. In this case, you see these four possible Bell states where they have the same probability to be created in the vertical and the horizontal in the first case, these 5 plus, which is called that they are maximally correlated. This minus corresponds to maximally anti-correlated, and then this corresponds to another process, a mixed process, where now you're going to have horizontal and vertical, or the opposite. The important thing is not only to generate this Bell state, but also be able to understand what it is and how they actually, you can grasp them in terms of the density matrix. In our devices, you can also perform tomography, and at the end, you can also obtain these really nice density matrices of the generated Bell states. What can you do with the Bell states and in our devices? Well, first of all, you can observe the violation of the Bell inequalities, or you can observe the non-locality, and also you can perform quantum chytrography, which is based on QKD protocols. In this particular case, the Bell state will help to conceive the Eckert protocol that uses the so-called Bell states. Now, let's go directly to our device, our entanglement demonstrator. Here you see on the left bottom part of my slide, the design, the picture of how it looks like. Here on the left side, we have our QEDU, which is the main controller of that controls all the motors, all the optical elements that are automatic, and also receives all the information, all the photons that are actually connected via optical fibers. And then here you can have either 2 or 4 single photon detectors, and of course, a time tagger. In this entanglement demonstrator, you can generate photon pairs, and then you can, of course, perceive the polarization entanglement of these generated photons. In this experiment, you can study the entanglement, you can study the violation of the Bell inequalities. Again, you can do the entanglement verification, and as I was mentioning at the beginning, we have multiple add-ons that actually can expand this whole universe of quantum experimental phenomena. Briefly, I would like to go very quick into the mechanics, what actually our entanglement demonstrator looks like. We have a laser diode, as I mentioned, center at 405. Here we have some mirror and lenses to redirect the laser light. This is our motorized wave plate that will change the polarization state of the incoming photon. Here are the BBO crystals. These are the YBO. One is motorized and the other one is fixed in order to generate the Bell states. And of course, we have 4 motor connector for the polarizers. This orange box corresponds to this our source, what I mentioned also in the animation. When the biphotons are created, here we have 2 mirrors that are going to redirect the photons into these fiber couplers. These fiber couplers actually are going to send the photons into our QEDU. We have polarized motorized rotation mounts where we have polarization filters, and then with this we can actually control, observe, make the bell in measurements, and here on the sockets, as you can see, you can introduce other elements in order to perform further experiments. What is our QEDU? Our QEDU is the platform for the quantum physics experiments. As I mentioned, it has inside, in these 4 single photon detectors, it has time tagging electronics. And with this, what is very important is that you can use multiple experimental boards, not only one. Here we have an example that we are plugging in an entanglement demonstrator, a nitrogen vacancy center board, and then you can simultaneously, either here in the QEDU or also be connected remotely with your computer, you can actually perform both experiments at the same time. And then this brings you also flexibility for an educator to have multiple students working in 2 different experiments or in the same experiment, but different boards at the same time. So I was mentioning, we have 2 perspectives. On the one hand, we have our GUI, which is an easy access, it's all the experimental or the physical phenomena is already almost there, just to grasp it by simple clicks on the touch screen. Or if you want to go a little bit higher in the possibilities of, or you have other ideas, what you can perform with our devices, you can go for the Python interface open source and then start manipulating not only the data acquired from our single photon detectors, but also manipulating almost all the optical elements in our setup in order to create different experiments. So what are the add-ons? Here I am showing you 2 pictures of how an add-on looks like. These are, of course, fiber coupled. So from our 2 fiber couplers, one can connect the incoming photons from the SPDC source to, for instance, our Michelson Interferometer. This is a Hongo-Mandel experiment, and this is a single photon interference Michelson Interferometer. So the available add-ons that we have is this Michelson Interferometer, the Hongo-Mandel add-on, where you can observe the Hongo-Mandel effect, the quantum key distribution, the Henry-Brown twist experiment, and lastly, the quantum state tomography, where you can, as I mentioned, you can measure the density matrix of the generated Bell states. In this presentation, I will very quickly go through the first 3 add-ons. So let's start with the Michelson Interferometer. Here, in this Michelson Interferometer, you will be able to understand and learn about the particle nature of photons. You're going to understand what is a quantum eraser, what is photon indistinguishability. And later on, if you want to go a little bit more advanced experiments, you can also perform the Franzen interference, which I will explain in a bit. So how does a Michelson Interferometer look like? On the classical side, here on the left, we have the wave perspective. In the wave perspective, if we have an incoming wave impinging on a beam splitter, what is going to happen is that the wave is going to be split into 2. It's going to be split into the transmission path and the reflective path. Of course, depending on the position of this mirror, we're going to observe either constructive or destructive interference. But let's go now a little bit further. What happens when a single photon is actually impinging on our interferometer? If the beam splitter is balanced, then we will have 50-50 probability that is either going to go forward or is going to be reflected. Particularly in our interferometer, what we have is that this incoming photon is diagonally polarized at 45 degrees. This is not a simple beam splitter, but a polarized beam splitter. So what it means that if we have a 45-degree polarization state incoming photon, is going to have 50-50 chances to either go forward or be reflected. So now we have here a superposition state of both. Actually, we have the same probability that both can happen. Therefore, the whole system and one single photon is going to interfere with itself, having, as I'm showing here, an interference pattern. Here I show you the single counts as a function of the position of the mirror in this case. What about a quantum eraser? So as I mentioned, here we have a 45-degree polarization state incoming photon, and we are able in our interferometer to introduce polarizers, one being in the horizontal oriented and the other one in the vertical. So now, if we put these polarizers, we're going to set to our system, we're going to now distinguish which photon is actually going out from our interferometer. It's going to be either horizontal and it's vertical. And if we can distinguish it, then therefore, and because the polarizations are orthogonal, therefore it cannot interfere. But what happens when we put an extra 45-degree polarizer? What is going to happen is that we're going to erase this information again. We will not know whether it's a vertically polarized photon or a horizontally polarized photon. Therefore, this is what is called the quantum eraser. And this quantum eraser is going to give us again the unknown criteria of the whole superposition system, and the photon is going to interfere again with itself. For the Franson interferometer, what we have now is that we need two interferometers. Now, it is very important that our source is a spontaneous parametric down conversion source. So we have entangled photons coming into our interferometers. And here, something very specific of the Franson interferometer is that we are going to have a short path and a long path at the output of our interferometer in both of the experiments. So when we align our two interferometers in a way that the short and the long paths are indistinguishable in time, we are going to generate a quantum state that is going to look as follows. Where here, again, we have a maximally entangled state of short and long photons traveling in these optical paths. And this is just an introducing phase of the interferometer. In this case, what we're going to measure and observe is that this is not only the common one photon interference, but here you're going to observe a two photon interference, or what is also so-called the non-local quantum correlations. Now let's go towards our quad-on Hongo-Mandel interferometer. In this add-on, you're going to learn about, again, photon indistinguishability in terms of wavelength, polarization, spatio-temporal modes, about the particle nature of photons, and here I am depicting the following scenario. Now we're having two photons impinging in a beam splitter. Before we only had one. And then here the inputs are in here and here. The photons are traveling from left to right, top to bottom. And then we have these four following scenarios. The first one is that both are going to transmit. The second one is that both are going to be reflected. And the third and fourth is going to be either one transmits, one reflects, or the opposite. But what happens if these two incoming photons are actually indistinguishable? If these two incoming photons are indistinguishable, what is going to happen is that we are not going to differentiate the scenario A and scenario B. Therefore, they are going to coherently superimpose, and it's going to only lead us to these two following scenarios. Either both are transmitting or one is transmitting and the other one is reflecting, or the opposite scenario. So in the case now that we want to measure coincidences of the output of these two the coincidences between these two outputs. Therefore, the coincidences basically are going to need to be equal to 0 because we don't have photons either here or here. Here I show you the Hongo-Mandel effect. This counts corresponds to the coincidences at the output of a Mach-Zehnder-like interferometer. And this is the time delay where we make the photons indistinguishable in every single property, in wavelength, in polarization, and also in spatio-temporal mode. So here, the photons are distinguishable because one is coming earlier than the other. But when we are changing the interferometer, what is going to happen, and specifically here, we're making everything equal, everything the same, everything is indistinguishable. Therefore, the coincidences are going to drop, and this is the so-called Hongo-Mandel dip. Why it's so important, or in other words, how can we use this quantum effect? We can use it in the so-called quantum optical coherence tomography. This coherence tomography, what it measures different layers of the sample of under investigation. The idea is that we want to make it as precise as possible, or to have as best resolution as possible. So with this quantum OCT, we have the advantage over classical technologies that we will have twice the actual resolution. And also, we're going to be immune to even order dispersion terms. Let's go to the last quad-on, which is the quantum key distribution. In our devices, what the goal of it is to explain and generate the two main protocols. One, the BB84 protocol, where you understand and learn what is a qubit, what is a non-cloning theorem, and on the other hand, the Eckert protocol, where you're going to use the entanglement of the generated photons, and also you're going to test the Bell inequalities. Here on the left down picture, I depict the main general idea of what is this quantum key distribution protocol is. Basically, you have a sender, which we call it Alice. You have a receiver, which we call it Bob, and then they communicate each other through a quantum channel. Let's have a look a little bit more into detail, because I know there's another webinar regarding this topic. But here we have a single photon source, which is Alice. Alice can prepare different bits depending on the polarization state of the photons, either vertical, horizontal, diagonal, or anti-diagonal. Bob also has a polarization system where he can choose how he wants to detect the photons sent by Alice. And this we call it the basis. So when Alice sends a bit sequence of zeros and ones, also Bob measures with its own basis, here drawn with different colors and different positions, either cross or X. These are Bob's results. Now with the classical channel, they compare whether if Bob or Alice, which times they select the same basis. These corresponds to these ticks. And then the resulting key corresponds to the bits that Bob measured with the same basis. Correct. So in our BB84 protocol, we do basically this scenario. We have Alice, we have our source, which is our QED source. We have Bob, we have our single photon detectors. Here you can see the basis that Alice chose, the bit values that Alice chose, what actually represents this M corresponds to minus or anti-diagonal, vertical, and so on. This is the detection that Bob observed, looking into its own basis. They compare the basis by a classical channel, and very important, they estimate the error. Because the whole idea of this protocol is to know whether someone is spying or not. And this will be known to looking into the error. If you don't have no errors, let's correspond that your quantum channel is safe. So in quantum communication, allows to transfer a secret key between two parties tap-proof. When the transfer of a secret key has happened, the message can be encrypted and sent via an open classical channel. But what happens when Eve is present? Eve can be someone that wants to get your information without being noticed. In this case, we have depicted what is the so-called intercept and resend attack. So Alice gets the photons from, Eve gets the photons from Alice, measures what is actually the photon, and sends to Bob what she thinks is the correct photon. Here we can observe the scenario when Eve is present, and in this case, the red lines correspond where, even though they chose the same basis, let's say here cross, they obtain the wrong value. Here the bit value is 0, here the detection value is 1. Therefore, that's an error. And the estimated error in this whole sequence was at 50%. Theoretically, the minimum total error probability that it can introduce is 25%. This because it has 50 probability chance to be either right or wrong. And also she has 50 probability chance to send to Bob either right or wrong. So when we multiply these error probabilities, what we have is a half times half, and this comes to a 25 probability of error when Eve is present. So if you detect a probability close to 25, then that means that maybe your communication has been corrupted, and therefore it is not longer safe to keep communicating between each other. And basically, this is what is the main idea of this BB84 protocol. With this, I would like to finish this presentation. Now I would like to continue with our live demonstration of our ED device, or entanglement demonstrator. So for that, I would like to now change my camera, change what I'm sharing. So first I will share different. Okay. And I will also change my camera. Let me see how it looks like. It's a little bit blurred. Okay. So that's why I spent a little bit of time to explaining what is the QED. So it's not confusing anymore. So this orange part corresponds to our source. This here is where the spontaneous parametric conversion process occurs. Here is the main UV laser, comes here. Here is where the two photons signal either are created, and with these two mirrors are redirected towards these fiber couplers. These are motors that we can control via our QEDU. What I am sharing in my screen is the software of our QEDU. So let's have a look. Here we have, we can have a look inside. What do we have here? We have 3 APDs. We have also a fast photodiode that it works for the nitrogen vacancy center. Here we have plugged the ED. This is basically the experimental description of what you're looking into in real life. And here you can see what is connected. I have connected also the Michelson Interferometer. These are the two polarizers that are controlled automatically. And then here at the top, this is where you can see and perform all the different experiments that we can see. So here we observe in time the single counts of the signal and idler photons in these two channels. Something that I want to show you is that these photons are polarized due to the type 1 process. So if I put the polarization, the incoming first photon or pump photon at horizontal, and let's say the polarizers are horizontal, then we're not gonna have anything. Sorry, I need to turn the laser on. So we don't have anything. But if I turn them vertical, what I see is that now I'm going to have much more light because the photons are polarized due to the process. Now I can do the opposite. And now again, I have light. So this is just to show you that everything is controlled automatically, and then you can already learn about the polarization state of the generated photons. Now let's have a look here into the photon pair alignments. Here we have a histogram as a function of the time delay of the incoming photons. And what you can see here is that basically this histogram reveals that the generated photons are being emitted at the same time. Here, this zero corresponds that this is what I told you at the beginning, the incoming photon gets annihilated and the two daughter photons are generated almost simultaneously. And this is basically what this histogram reveals. Here I have the single counts of one channel, the coincidences counts in the middle between channel 1 and 2, as you can see here, and the single counts of the second channel. Now I want to show you our single photon interference. Let's have a look. As I mentioned, this is a self-guided experiment. Here, as you can see, we have different resolutions that you can perform. And actually here, I need to change the polarization state, sorry. This is channel 2. So let's go. Yeah, I need to refresh it. So as we can see, we can clearly observe already the single photon interference pattern created in our Michelson Interferometer. I would like to turn my camera and you can observe what is actually happening in real life. So now with my hands, I will guide you through the experiment. So this is the incoming light. Here we have the two mirrors. So the photons are going to be reflected back again to this polarizing beam splitter. And then the photons are going to travel towards the single photon detectors. Now, something interesting is what happens when we compare the interference pattern of, at the bottom, single photons and the interference pattern of the coincidences between the photons. What you can observe, maybe right now it's not super clear, but what you can observe is that the coherence length it's broader than the coherence length of a single photon. And this is due to the generation process of the entangled photons. Due to the quantum process of how the photons are being generated, therefore, the coherence length of the two of them is going to be larger than the coherence length of one single photon, as you can see here in these measurements. I would like to finalize my live demonstration by the quantum eraser experiment. Here again, if you look at my camera, here we have these windows where I'm going to close them. And these windows basically correspond to the polarizers. This is a polarizer in the horizontal direction. This is a polarizer in the vertical direction. So now I will erase what we are looking so it's clearer. I am scanning in the same area, as you can see. And then what is basically happening, first of all, yes, we have less counts because some absorption of the polarizers. But what is most importantly and clear is that we don't have interference. That means that we are telling the system, or we are actually obtaining the information of the system from which arm the photon went. But what happens when I close this last window, which corresponds to the 45-degree polarizer? Now you will observe, now I will clear it again, then the interference is going to happen again. And then basically just to finalize this experiment, what we are looking at is that we are erasing again the information of which path the photon took, and therefore we are making it a superposition state, and now the single photon can interfere with itself. So with this, I would like to finalize my presentation. And of course, if you have any questions, I will be very glad to answer them.
Thank you, Santiago. Participants, you can ask your questions in Q&A box, and we will reply to it. Thank you.
I see a question. I will read it. Is the quantum eraser basically a Hadamard operation? Can you explain a little bit more about the Hadamard, like mainly, or maybe with the name, I don't recall it, but if you explain a little bit more, then I can answer it. Does this equipment covers most of the quantum experiments? So thank you for the question. This equipment, so the add-ons that I was explaining, they come separately. So the main device is the QEDU. We can sell the QEDU and the quantum demonstrator. If you want to perform different experiments like the Hongo-Mandel experiment or Michelson Interferometer, this is the so-called add-ons, and then they are separate, and of course they are covered for undergraduate students. The whole idea of, or the whole vision of our company is to expand to every single level. And that's just the flexibility that you have with our devices, that you can start from the basic to the very more into detail explanations of what is actually happening in the quantum phenomenon. So in the third question is what happens if the error goes further than 25%? So in this case, basically, there is a probability that the communication is not longer secure. So in the continuation of it, then one should actually observe all the communication, the physical communication path. For instance, nowadays, how people communicate is with optical fibers. So you will have to check in your old optical fiber whether someone is actually cutting the fiber and trying to intercept your data, your communication. In this case, yes. If it's more than 25, the most secure thing to do is to discard not only the key, but the complete communication and revise and check what is actually happening. Because can be also that the error is happening because something else. But then a key point is that the communication between Alice and Bob is compromised. Next question, with add-ons, what are the number of experiments can be covered? Does it cover quantum algorithms? The number of experiments that can be added with the add-ons are basically 5, which are Michelson, so not the number of experiments, the number of possible experiments, which is interferometer, Hongo-Mandel effect, Henry-Brown twist experiments, tomography, QKD. Basically, these are the 5. But in these 5 add-ons, one can perform other experiments. For instance, with the QKD, this is what we're developing. Is either you can go for the Eckhart or the BB84 with the interference with the interferometer. You can perform quantum erasement or just observe single photon interferometry. Does it cover quantum algorithms? Not yet. The quantum algorithms is not involved yet, but this is something that if there is a way or you have any idea that already with the data that you are collecting, you can perform an algorithm, then as I mentioned, it's definitely possible using our Python codes. And then therefore you can manipulate the data and then you can start to construct these algorithms. Let me read the next one. The Hadamard basically restores the superposition state when acted over an already collapsed state. For example, an upspin electron after Hadamard will become a superposition of up and down spin. So this is what is happening. Yes. Yeah, basically, this is what is actually happening. I'm reading the next one. So you have different add-ons unit for different experiments, like for Bell state, quantum state tomography, HBT. For quantum state tomography, the half-wave plate and the quarter-wave plate are controlled using GUI with use of motorized mounts. Yes. So in this case, right now, I only show the polarizers, the motorized polarizers in front of the fiber couplers. But as I was telling you, there are sockets in front. What we do is that we only introduce quarter wave plates. And then with this, we can manipulate the whole quantum state tomography for 1 qubit and 2 qubits. So you can have the complete density matrix, and everything is controlled via motorized mounts, and it will be just done by a simple click on our GUI.
Any other questions?
Can you explain how H and B states are d-phase when incident on the crystal of the half-wave plate? Yeah, so basically, let's think about, it's all about birefringency. In this YVO crystal, what we have is that depending on the optical axis of this YVO crystal, the light will see different refractive indices, whether it's vertical or horizontal. So if in the vertical orientation, the light observes a higher refractive index with correspondent to the orthogonal, therefore the light is going to propagate differently. So at the end of the state, what is going to happen is that the H and B states are going to be dephased in time, just by the birefringency of the crystal. Another question. Can it be used for mathematical operations in using qubits? The question of can it be used for mathematical operation synthesis using qubits? Can you say what? Like the previous questions or previous, to be more specific, please. The maximum laser power, it's around 50 milliwatts in the UV laser. Yes, there are intership positions, and then you can. So the question is if there are internship positions available. Yes, we will, and then you need to contact us, and then we can actually look at it. Let me think about it. I'm just thinking about the last one. This one, I am not completely sure, so I don't want to respond now, but definitely I will keep it in mind, this question, and gladly I can answer you via email. If uh, I will have this I will have to double check about this. I am not 100% sure, and I want to investigate a little bit further. Another question. Single photon detectors are within the source unit. How are they isolated for ambient light for out of the lab demonstrations? So basically we have interference filters in front of our fiber couplers. So especially, first of all, we have single mode fibers, which are around 8 microns, like the tip of the fiber. And with this, basically with these filters, we neglect a lot of light from the ambient side. For instance, here we are in our demonstration room, and then basically there's a lot of light. Nevertheless, it's safe for the single photon detectors. In this case, the either and signal difference was due to some alignment. Normally, the whole idea is it's about to make them as equal as possible. Of course, we also have different quantum efficiencies in our detectors. Therefore, of course, we will have a little bit of difference between the two of the channels. Nevertheless, the heralding efficiency right now, you can perform this in our Henry Brown twist experiment, where we perform triple coincidences. And then basically what we do is that in one channel, we connect them directly into the detector one. And then in the second channel, we split them into two. And then we start to perform heralding coincidences or triple coincidences. Right now, I don't have a solid number to tell you what is the efficiency, but our photons are very well isolated from the frequency that we want, which is centered at 810 nanometers. And therefore, we take care a lot of fluorescence processes that can occur due to the UV laser. We know that the UV laser generates a lot of a lot of fluorescence when interacts with lenses and crystals and so on. Nevertheless, we have a very good heralding efficiency. I would say higher than 80%.
We can like any other questions, or we can end this webinar. And if you have any other queries, you can reach out to us. And I'm just sharing my our email ID, so you can just share your queries and request, so we can reply to that. So you can mail us at support@digitotech.com, and you can also contact us. You can visit our website as well. And if you want any quotation regarding queries you have, or any other discussion you want to have, So we can arrange a similar kind of a meeting, and we will be there to support you. And yes, after this webinar ends, in few days, like in 1 or 2 days, we will be sharing you the webinar's recording. You can also visit that recording, and you can also share with your students or any other professors as well. And we are also planning to have a webinar next month, mostly next month, on quantum key distribution. So we hope you register, and looking forward to it. So thank you all. Thank you, Santiago, for your time.
Thank you very
and
much
for a
for the
very good
invitation.
presentation. And thank you so much, all the participants as well. And looking forward to collaborate soon. And we will be updating in our social media site. And also, you can also see the updates in our website page. So thank you for your time and joining.
Thank you everyone for joining and for the invitation.